well, welcome everyone. I think this is our last TCS Plus talk for 2025. So, um, yeah, well, welcome. And let me introduce our speakers today. So, it's a great honor to have Natalie Collina from the University of Pennsylvania, who's been doing a lot of really fantastic work on games and algorithms and theoretical computer science. And so today she'll tell us about swap regret and correlated equilibria beyond normal form games. So before I hand over the floor to Natalie, I do want to encourage everyone to keep their cameras on. This makes the talk for Natalie like a little bit more engaging. And feel free to ask questions, either unmute yourself or in the chat. I'll also be monitoring the chat. And then toward at the end of the talk, we'll have an unrecorded session with Natalie where we can just ask her all the hard questions that we were maybe too embarrassed to ask during the
Mm.
talk. Um, but with that being said, I also want to say that if you have any suggestions for talks that you think would make great TCS Plus talks, we always welcome suggestions on our website, and we take these very seriously when inviting people for the next semester. All right, so I'll hand over the floor to Natalie, and yeah, please take it away.
Wonderful. Thank you so much, Eric. So today I'm excited to talk to you all about swap regret and correlated equilibria beyond normal form games. And this is joint work with my excellent collaborators, Ishwar, Yishai, Marier, John, and Valu. And yes, please feel free to unmute yourself and ask questions. I'm very happy to stop. I don't want to move on from something and have people be confused because I think it's more important that that the things that I say are clear than that I get through every single beat in the talk. Wonderful. Okay, let me start by just giving you all the upshot of what's going on here. So I'll talk more about what this is later, but no swap regret algorithms are these types of algorithms that have really nice and fundamental properties in strategic environments, specifically in repeated normal form games. But it wasn't clear how to get that same strategic niceness in more complex games like Bayesian and extensive form games. It wasn't clear how we should define swap regret in these settings. So what we do in this paper is we define it. We come up with a new notion of swap regret that actually does guarantee these nice strategic properties and show, which was not known whether it was true or not, that not only does this notion exist, but it can be efficiently minimized. There are algorithms that exist that can minimize it. And as a fun little bonus that I'll get to at the end if we have time, this suggests that there's two different views of correlated equilibria, and they seem like they're the same in normal form games, but they're not fundamentally the same. It's in some ways a coincidence that they're the same. And when we go beyond normal form games, they become different equilibria notions. Wonderful. So now that we've talked about the upshot, let's back up and get to some fundamentals. What are repeated normal form games? So let's look at an example. Here we have me, Natalie, and my wonderful co-author and friend Ishwar, and we are both trying to sell coffee. And perhaps our options are how should we price this coffee? And to simplify things a bit, imagine that we have three choices. We could all price it $1, $2, or $3, and maybe our coffee is exactly the same. So all that the buyers will care about is how expensive our respective coffees are. So as you can imagine, this defines a game where if we set the price lower, then people are more likely to buy from us, right? Maybe if I set it at one and Ishwar sets it at two, they buy from me, but I'm going to get less money than if I'd set it higher and they bought from me, right? Okay. So that could be a game that just happens in one period, but of course, realistically, people sell things not just once, but many times. So we can imagine having a repeated normal form game um, where every day we both choose simultaneously a price, and we can keep doing this, and they can vary over time. And the outcome, how happy we both are, or utilities each day is determined by not just our own price, but the other person's price as well. But increasingly, people aren't just pricing in repeated settings like this, like choosing a different thing every day. They might use algorithms to price. So you can then ask, what if Natalie wants to use an algorithm to play this game? So what does that look like? So let's look at some examples. Natalie could price at $1 for odd rounds and $2 for even rounds, right? So she could employ an algorithm that's time varying. She could, I don't know why I'm saying she, it's me. I could price at whatever Ishwar's price was yesterday. So I can be adaptive to the behavior of the other agents in the game from their previous time steps. And I can use randomization. I could flip a coin to choose between $1 and $3 every day. So these are all tools I can use that I can incorporate together to come up with an algorithm, just to give a sense of the breadth of what's able. In general, I'm just, you know, mapping from the previous actions of the other person to the actions that I'm taking the next day, or a distribution. Um, so given that, you can then ask, what is a good algorithm for me to play? Now, there is an answer from this from online learning, which is that no regret algorithms have a really great general guarantee. A no regret algorithm gives guarantees beyond just strategic settings. There are algorithms that give guarantees in sequential settings where you just take an action and see a loss. That loss doesn't have to be from some strategic component. But the guarantee that you get is quite strong, which is that if you run a no regret algorithm and then you kept the loss factors or the actions of the other person fixed, and I thought about, would I have rather played some single action the whole time? So instead of just this sequence, given that Isha was doing this, I could have played $2 the whole time or $1 the whole time. It should be that none of these are better than what I actually did. So that's what external regret is. It's the regret, the amount that I would have gotten if I had swapped to the benchmark of my best fixed action all the time. Okay, so before I move on, does this make sense? Does anyone have questions on what no regret means?
Um,
Is that a question?
are there any guarantees
Are there any
like
guarantees, you said?
competitive ratios?
So the guarantee that a no regret algorithm gives is that even if the adversary is specifically trying to maximize your regret, even if their goal is to say, I want to play a sequence, knowing the distribution they're going to play every day so that I maximize their regret to the best fixed action, they can't do it. That's the guarantee that no regret algorithms give. It doesn't, I guess, by guarantee, if you mean are you guaranteed some particular utility? The answer is that no regret algorithms don't guarantee that because the adversary could, at least in a general loss setting, just give losses of zero for all actions forever. But you don't have regret then because there's nothing better you could have done.
Thanks.
Yeah, thanks for your question. Okay, so we're interested in a refinement of no regret. So we've just defined no regret, but actually we're interested in a stronger benchmark than that, which will be useful for this talk, which is no swap regret. No swap regret, it's the same general setup. It's a guarantee on all possible sequences that could happen when you play your no swap regret algorithm. And it says that, okay, keeping the opponent's actions fixed, I then will swap, but my new benchmark is for every single subsequence in which I play the same action, I need to be competitive with the best action on that subsequence. So swap regret means I can swap all these blue ones, the ones where I do $1, to the best price on that subsequence. So I can switch all the times I did $2 to the best thing on that subsequence. I can switch all the times I did $3 to the best on that subsequence. And still, I would like it to be that even if I do these swaps optimally, I am not doing any better than I was before. And amazingly, this is still possible. So we can still do this efficiently. At least if you do a repeated game, the regret that you have to this benchmark is going to be sublinear in T. So as T gets large, the average swap regret goes to zero. And to be clear,
Can
is
I
there a
clarify?
question?
Yeah, sorry. There should be a bijection between the actions, right? Like it's not like you could map every action to $1 and kind of recover no external regret.
Um, when you say there should be a bijection, so you could map every action to $1, no
Okay.
swap regret is a stronger notion.
Yeah.
So, in particular, if you have no regret, you certainly have no swap regret because one possible swapping is every action to $1.
Okay, cool. I think I always get confused with the misnomer of swap.
Yeah, yeah, that's fair. Right. It's a refinement. It is strictly more powerful guarantee. Um, okay. Yeah, it doesn't have to be bijection. So,
Sorry. Also,
right.
Natalie, the
Yes.
these subsequences, it it's defined by all the subsequence where you played the same action, or it's a consecutive
Mhm.
subsequence of that same action. So is it
Great.
important that okay, yeah, maybe you should.
Yeah, thanks for the opportunity to clarify. It doesn't matter that it's consecutive. So here, if you look at this picture, right, the things that are in blue, those are the same subsequence. Uh, it doesn't matter that they're not consecutive, right? I'm saying that all the things in blue, all the times that I played $1, those times, I need it to be that on average, $1 was the best price. Does that make sense? So consecutiveness is not important.
Okay. See.
Great. And I gave this example just looking at, deterministic prices every day. But in general, I could have instead played distributions. And the notion of swap regret extends linearly here. So for example, if on this first day I'd played half 50% time $2, 50% of the time $1, then what I would do is I would sort of include that day in the $1 subsequence with like a half weight, and in the $2 subsequence with a half weight. So there's a natural way to extend this to distributions. Okay. So now that we've talked all about that, I want to say, well, these properties, while they're nice and very cool to have in general in online loss scenarios, they're not completely satisfying on their own in these game theoretic environments that I started the talk defining. And why is that true? These guarantees are things that hold for any sequence of losses on what I'm playing, which is so cool. But we actually have a more structured environment than that. What we're imagining here is that we have, say, Natalie as the learner, and I am committing to a learning algorithm. And Ishwar, as an optimizer, is going to look at that learning algorithm and then figure out a best response in algorithm space to this algorithm, saying, okay, I see this thing that you're playing. What's my favorite sequence to play against it that maximizes my utility overall? And so we want guarantees against someone like Ishwar, who's strategically optimizing for their own utility. Okay. So what more can we get in this sort of environment? This is the setting that we are curious about. But by the way, these notions I just described are going to come back. So don't worry that we wasted our time talking about them, but they're going to come back in surprising ways. So we can then ask, okay, in this sort of setting, what are some good things that you might want? And one notion, which seems valuable, is it's probably nice to be able to characterize the types of algorithms that can't be manipulated by a strategic optimizer. And here by manipulated, what I mean is that there's no time varying sequence of actions that Ishwar can play against my algorithm that does better than just some fixing the whole time. So specifically, the best algorithmic response to a non-manipulable algorithm is a static strategy. So it could be randomized, it could be a distribution, but if it is, it's the same distribution every day. So does that notion make sense? What a non-manipulable algorithm is? Okay. So as an example, if I'm playing a non-manipulable algorithm, and Ishwar is thinking, okay, well, I'm not myopic. I'm thinking about the whole space of time, and I want to think about what to do. it's still true that he might as well play the same price distribution every day. So, for example, maybe it's $1 every single day. And there's lots of nice things about non-manipulable algorithms, right? Just clarity on what the responses might look like for the learner and the optimizer. But it also does have a connection to welfare and utility of the person deploying it. So, for example, in a repeated auction setting, if the bidder is running an algorithm that is no regret, if it's also manipulable, then the auctioneer can always extract full welfare from the bidder. So this is, without getting too much into auctions, just giving some intuition that, okay, there really is a connection between manipulability and the utility of the person deploying the algorithm. Okay. So say that you're non-manipulable and you have no regret. If you have both of these properties together, then you also get something quite nice, which is that you are guaranteed your Stackelberg follower value against any strategic optimizer. Now, what is the Stackelberg follower value? So the Nash equilibria is an equilibrium where two people at the same time commit to something, and then it's only a Nash if they're both best responsive to each other. Stackelberg games, one person goes first. So the notion is you have one person commit to some distribution of actions, and then the other person goes second in best response. And the question now is, it's an equilibrium if the first person commits to the optimal thing conditional on the second person best respond. So the difference now is that the first person doesn't actually necessarily need to be best responding to the second one. Anyway, all that is sort of an aside just to say that there is this well-defined equilibrium notion where the Stackelberg follower, where if you are a non-manipulable and no regret algorithm, you are guaranteed a utility in accordance with this equilibrium notion. Okay, no swap regret algorithms are non-manipulable. So this is great. So we've been trying to figure out now. We're like, okay, no regret algorithms, non-manipulable algorithms, both have some nice properties. One of these is nice in general. One is specifically nice in the strategic setting that we're considering. And it would be nice to look at the intersection. And the answer to what this intersection is it is exactly the set of all no swap regret algorithms, at least in normal form games. So everything in the intersection is no swap regret, and everything that has a no swap regret property is in that intersection. This is cool, right? So if I want to have a no regret, a non-manipulable algorithm, I can just take any no swap regret algorithm, of which there exists a couple different kinds of different flavors, and they run efficiently, and I can just take it and I can run it. Okay, so that's great. For repeated normal form games, this is great news. But that's not the only sort of strategic environment that is important. What about repeated Bayesian games? This is a more complex sort of game compared to a normal form game. And now we'll explain an example. So maybe some of you were thinking when I was talking about this pricing game before that I was missing some nuance to what was really happening, which is the cost of production, right? So, the coffee isn't free for either Ishwar or me to produce. So there's some other context involved in this interaction, which affects what the outcome is. So now let's imagine a more realistic version of this game, where in addition to choosing prices for our coffee every day there's also a context, which is what the cost of production for coffee is that day. So for example, maybe on a certain day, there is some sort of trouble with the assembly line or something. So coffee is more expensive to produce. And maybe there's some exogenous distribution over context. So I don't know exactly what the distribution will be to what the context will be tomorrow, but I have some prior over it. So now we can ask, what is the strategy now? Before the strategy, every day was just a price. But now the strategy every day, even just in a single day, is a mapping from context to prices. So here I'm representing that by showing this little table where on the left side we have the context, on the right side we have what price is being used in accordance with that. So we can again go back to saying, okay, great. Like it would be nice to, in this setting, now think about what swap regret means so we can recover these strategic guarantees we've discussed. So we can ask, what should we swap here? And this is the way that people have previously tried to tackle this problem. And so let's start by discussing why that's a hard question. So what should we swap? And if anyone has any suggestions, audience participation time, now that we have this as the object, what do you think is the unreasonable notion of what we should swap? So one thing that we could swap is we could try to swap the entire mapping structure, right? In some ways, that's the most natural allegory to the normal form setting. Your new action is this mapping. So maybe I take this entire mapping and I swap it to other mappings. So I say all the times I use this specific mapping structure, I swap to the optimal mapping structure on that subsequence. So for example, here you can see these first 2 days, I'm actually playing the exact same mapping structure. So this is one subsequence, and then these are two completely different mapping structures. And that would work. This just sort of takes this Bayesian game, turns it into a normal form game. You could do this. And it gets you this non-manipulability and no regret guarantee. But the problem is that the number of different subsequences now blows up exponentially in the number of contexts. So we lose the ability to have tractable algorithms for this. Okay, here's another idea. So
Sorry,
remember I said, yes.
there's a question on the chat.
Oh, sorry, I can't see the chat. Go ahead.
I can read it out to you. So Sebide is
Thanks.
asking, where did you get the static answer for the previous case?
Where did I get? Sorry.
Or maybe Sebide, you can unmute yourself and
Yeah, what case? Maybe that was a little while ago,
The
or
normal form, I guess, the one before
yeah, yeah.
the context and stuff.
What slide? What do you mean by static answer?
We just reduced the current solution to the previous one, but you didn't. You said there was a solution for this one, but you didn't explain where it came from. The previous slide, I think.
Oh, so you're saying, right. I think correct me if I'm wrong. I think your question is, what is the algorithm that achieves no swap regret in normal form games? Is that the
Yes,
question?
exactly.
Okay, great. Yeah, that's a great question. So, it is not. So, right. So there exists these algorithms. I can give some intuition as to what they look like, but they actually are, while they run efficiently in the parameters, they are sort of tricky algorithms. So, in general, let's start with no regret. No regret algorithms look a lot like just playing the best action in hindsight and adding a little bit of noise in a carefully chosen way. That's enough to get no regret. If you want no swap regret, you actually you have to do something a little trickier. The classically most common algorithm for no swap regret basically solves a fixed point computation, an efficient one, but still a fixed point computation at every round of the game. And so it's something that is, yeah, it's a little tricky to explain. And unfortunately, I don't have the slides for it here. I'm happy to, talk about it more at the end of the talk. But the idea is that instead of just having to solve a no regret, like basically what it does is you employ a bunch of different no regret algorithms, and then you maintain some weights over them, and then you solve a fixed point computation over those weights at every time step. Cool. Okie dokie.
Does it always
So,
exist?
yes. So in normal form games, this algorithm that I just proposed always exists. It can always guarantee a vanishing swap regret as t gets large. Yes, as long as the number of actions is finite, this gets the t to the 2/3. If the number of actions is infinite, then actually in some settings, we still have algorithms that work. But if you're in an infinite, if there's an infinite number of actions, there are some times when it's not possible.
Thanks.
Thank you. Okay, so another thing we could do in terms of swapping is we could say, okay, remember that actually we had this exogenous distribution over context. And so for every single mapping structure, this actually induces a distribution over action. And so we could look at our mapping structure, apply this distribution over context, and look at the resulting distribution over actions, and then apply no swap regret to this distribution. And remember, we know how to apply swap regret to distributions. And you could do this, but actually this is too weak. So this doesn't achieve non-manipulability, and it doesn't even achieve external regret to the best mapping structure. So what we've just defined is one way of swapping, which works, but it's too computationally complex. One way of swapping, which doesn't work. Okay, so we need something in the middle. And we actually need new tools to think about this. So now I'm going to talk about this new tool, which we call a menu, the menu of an algorithm, which is a geometric interpretation of algorithms for repeated games. This tool ends up being really interesting and useful in lots of applications, not just this result I'm talking about now. If you could think of other ways to use it, part of the goal of this talk is not just to talk about this main result, but also to introduce this notion of menus for algorithms to a wider audience. So just to, again, remind us what we're looking at so we can embed this notion of menus here. We have a learner, and they're playing a distribution in every round, xt, over some n actions they have. And the optimizer plays yt, a distribution over n actions in the tth round. And both of the players have bilinear payoffs. It's a normal form game. So what normal form game means is that the utilities are just dependent on your action and the other person's action. Okay, so I will now talk about how we get to menus. So typically when we think about algorithms, right, I talk about them as mappings from history to distribution of our actions in the next round. And so if you wanted to, you could now think of this as a sequence of all possible transcripts of play. So every transcript play is depending on what the other person does in the game, this is going to induce some transcript, right? So I could imagine, okay, take every single possible sequence of actions that the optimizer could play. Let's write them all on a transcript, and this defines my algorithm. This is a quite large object, but I could do this. So for example, like already you can see things happening here. So if you had a no regret algorithm, then this set of possible transcripts of play must be entirely composed of transcripts that satisfy this no regret property. Okay, so that is fine, but it's a way too large of an object to understand algorithms through. So given this transcript, we are going to compress it. We are going to take a transcript, a free transcript, compress it into a correlated strategy profile, which is the empirical distribution over action pairs in that transcript of play. Right, so let's think about what happens here. So if I have a transcript, right, so remember what a transcript is. It's t different action pairs every day, or rather pairs of distributions of actions. So what I'm going to do, excuse me, is take this transcript and smush it together so that there's no notion of time or order anymore, and I'm just preserving the relative distribution over these action pairs. So what do we preserve when we do this? Certainly we lose some things. We lose order. We preserve the payoffs of both the players in the game. Because remember, all that is determining the payoffs is at every single moment what I do and what the other person does. So if I'm keeping this imperial distribution over action pairs, I keep the payoff. It also preserves the regret and the swap regrets. Why is that true? Well, again, these are notions that depend, even swap regret, the more strict one, only on the number of times that I did something and when I was doing that, what the other person was doing. It didn't matter what order it was in. It didn't matter when in the game it was. And for those of you this is useful for, this distribution of our action pairs is the same type of object as correlated equilibria. Okay, so let's give an example of how we go from transcripts to CSPs. So going back to this transcript, I can say, okay, here's one transcript. What is the CSP of this transcript? Well, you can see that half the time I'm pricing at $1 and so is Ishwar. So if we look at the joint distribution, half the time it's 1, 1. We can see that a quarter of the time I'm pricing at $2 and Ishwar is pricing at $1. And then the remaining quarter of the time, we're both pricing at $2. So this would be the CSP of this transcript. Any questions about CSPs? Okay, great. So now let's take this idea and
Wait, sorry.
apply it.
How do you
Yes,
how do you choose Ishwar's actions?
great. So I'm not choosing them here. I am simply saying take a generic transcript. How do I turn it into a CSP? But this is going to be relevant because going back to this notion, we're going to use this to look at all possible CSPs that Ishwar could possibly induce against my algorithm. Does that make sense? So the answer is I have no control over it. He could play any sequence he wants. And I am curious about what the space of outcomes that could possibly induce against my algorithm are.
Okay, sure.
Cool. So now if I look at an algorithm, I could ask, what is the set of all possible CSPs that can be induced by Ishwar? Not even necessarily Ishwar being strategic at this point, just he could come up with any sequence of distributions. When he does that, what are all the possible CSPs that we can get? And like, we'll look at some examples of menus, so you'll get a sense that, depending on the algorithm, these can really be different. Okay, right. So what is the menu? The menu is the convex hull of all such CSPs that can be induced by playing against our algorithm. So every single algorithm for a repeated game has a corresponding menu. And this menu is a geometric object in the n times m dimensional simplex. Why is that true? Well, the CSPs themselves are distributions over action pairs. And I use n and m to be the number of actions of each player respectively. So if we take the convex hull over these, this is a object in n and m dimensional simplex space. Okay. And even more formally, because of course games can have very different lengths of time, the way that we define menus is we take an algorithm, and we generally think about algorithms as either taking the time for the game at the beginning or running for however long it wants to. And then we say, okay, I'm going to look at the menu of this algorithm at if the game is length 1, if the game is length 2, and I'm going to look at the limit menu and say that that is the menu of this algorithm. Now, you might ask, does that always exist? And the answer is no. You could, define algorithms where the limit menu does not exist. So what we're doing here is we restrict the learner to playing only consistent algorithms. So algorithms in which the limit menu does exist. And it turns out this is not too big of a restriction. Many natural algorithms are consistent, including our hero of the story, no swap regret. So now let's give an example of menus. So say I have a learning algorithm, and the game is that I am allowed to play actions P or Q, and then the action set of the optimizer is A or B. And my learning algorithm is, no matter what happens, I am always playing P. So we can then ask, what is the menu of this algorithm? Does anyone have an idea of what the menu of this algorithm is? Or like, what are some CSPs that are in this menu?
The optimal static one from before? No.
What do you mean by the optimal static one?
And the one you said, oh, that was for a normal phone. Yeah. Sorry.
Oh, no, it's okay. This is
The
normal. So actually, just to
optimal
be
one,
clear,
maybe.
we are in a normal form setting right now. So the thing I'm describing right now, this is normal form right now.
Okay,
So
so what I understood from CSPs was that you had the optimal solution, but it was a static one, and you used it to learn or summarize the other thing, and then mapped it here, or
So,
did I understood it all wrong?
um, so we are at this point, our goal is not to guarantee. I guess I'm not totally sure what you mean by solution, but I think the solutions I was talking about before were about swap regret. Our goal here is to understand what outcomes are possible to induce if the first person commits to a learning algorithm that always plays P. So let's talk about what that looks like. So if the learning algorithm says always play P, and then I'm playing against that algorithm, like what is it possible for me to induce? Well, I can't induce anything that includes the action Q, right? Because the learning algorithm just doesn't have an outcome where it allows it. But I can do anything between A and B against P. So the menu here is the convex hull of A with P and B with P. Does that make sense? Okay. Going to move to another example that's a little trickier. Say that a learning algorithm plays Q as long as the optimizer has always played A, and otherwise it plays P. Okay, so what's the menu here? Now we have an algorithm that's more adaptive, and we can think about what are the possible outcomes that can be induced by any optimizer against A2. Okay, so let's think about the points that should exist. Well, one thing that the optimizer could do is play A all the time. If they did that, then the outcome would be the product distribution of Q with A. So that should be in the menu. What else should be in the menu? Well, the optimizer could immediately start playing B and do that forever, right? And then it'll be B and P. But the optimizer could also, after playing B for some amount of time, even just one round, immediately switch back to A. And so because of that, A and P is also in the menu. So this is the menu. Now you might if in the very first round, for example, the learning algorithm starts playing Q, and in that first round, the optimizer plays B, then why is BQ not in the menu? And the answer is because we're only concerned with the limit menu. And in the limit, the ratio of times that this one round happens goes to zero. Okay, so what are some nice properties of menus? So menus are upwards closed. So what that is, if I have some convex set, which is a menu, aka there is an algorithm that's the set of all outcomes associated with it is this menu, then if I took a set, which is a superset of the set, there's also an algorithm that has this set as its menu. Why is that true? Okay, well, here's how you see that. Here's what the algorithm is. First, it's going to use a sublinear number of rounds of communication to ask the optimizer whether they want to play any of these additional points that we've added. If they say no, or if at any point they stop playing along with these points, the algorithm is going to defect to playing A1 and with a history cleared. So what this means is the algorithm has made these extra points a possibility, but also everything in the original menu is still a possibility. And menus also have this really tight, interesting connection to approachability. For those of you who are familiar with Blackwell approachability, I'm not going to have time to explain in depth what's going on, but I really encourage any beginning PhD students to learn about Blackwell approachability. Blackwell's a really cool guy and solved a lot of the stuff. I think a lot of the work that many of us in learning theory do is figuring out, oh, did Blackwell already solve this, and how can that be applied to the thing I'm thinking about? So there's this really nice notion called Blackwell approachability, and it turns out it has this really nice connection to menus. And that a menu, some convex set is a menu for some algorithm, if and only if it is approachable in this Blackwell sense. And I think in the interest of time, I will skip this, but happy to talk about it later. Okay, so menus are all you need. So going back to the notion of menus, remember that the convex hull of all CSPs that can be induced by playing as A is the menu, and that this retains the utilities. So what that means is that we have this convex set, and you can think about the utility of the optimizer and the learner as being vectors in the same space, because they're also just dependent on this distribution over move pairs. So we've dropped some information, but we've simplified the problem by preserving only the outcomes, even if we don't know exactly how to get them. And really importantly, now that if we have the menu of an algorithm, we know that a rational opponent, an opponent who has tried to not non-myopically optimize against my algorithm, is only going to pick extreme points of this menu. Even if I don't know my opponent's utility, I still do know that all the outcomes they'll induce are going to be some extreme points of my menu. Why? Because whatever the utility of this optimizer is, it's some direction. It's pointing somewhere. And so it's not going to be the best income is not going to ever be in the middle of the set. It's going to be on one of the edges of the set. It's going to be some extremal point. Okay, so this gives us another way to view no swap regret algorithms as non-manipulable and no regret menus. So a no regret menu is a menu that has it's the menu of some no regret algorithm. And so, of course, all the points, all the CSPs involved have to be no regret. And what makes a menu non-manipulable? And this is really important, kind of key to our insight in this paper. A non-manipulable menu has to have extreme points that are all product distributions. Okay, so why is this true? And note that in general, it's not true, right? So CSPs don't need to be product distributions. It could be a correlated distribution between, it could be half the time price one, half the time price two, right? That's not a product distribution. So why is this true? So remember that an algorithm is non-manipulable if it best responds to the static strategy. And so why is it true that all the extreme points of the menu need to be product distributions? Assume for contradiction that it's not true. Okay, so now take some extreme point of this menu, the one that is not a product distribution. Well, there could be some utility of the optimizer. There must be some utility of the optimizer such that this extreme point is the one that optimizes their utility. And because it's not a product distribution, it's not possible to realize this point by the optimizer playing the same distribution every day. So the optimizer's best response will be time varying. Therefore, this is not a non-manipulable algorithm. Okay, so keeping these two things in mind, how do we think about no regret and non-manipulable menus? Well, they have to only include extreme points of that form. And in particular, the claim is that the product distributions that are the extreme points are all of the form of some distribution y from the optimizer, and then some best response to this y from the learner. And the reason this is true is because we already know that these 3 points have to be product distributions, and they can't just be product distributions. They have to be product distributions that have the no regret condition. And when you apply the no regret condition to product distributions, it's very straightforward. If it's a product distribution, then you simply need to be best responding to the whole thing the other person's doing. And so that tells us that every point, that the extreme points all must be of this form, but we also need to include everything of this form. So what that means is that all no regret and non-manipulable algorithms actually have the same menu. So this unique menu is the menu of all no swap regret algorithms. So thinking of strategic menus gives us a nice alternate pathway to think about no swap regret. And this ends up being really important for polytope games. And what is going on with polytope games? Now, in terms of time, I am sort of running out of time, but you should be slightly less concerned than you think, because actually, we've already solved things for polytope games already. We just don't know it yet. So what is a polytope game? It's a generalization of Bayesian games, right? So it's this thing going beyond the outcome just being an action pair. Um, More generally, it's about polytopes. So in a normal form game, the actions that you can pick every round are in this simplex. You pick a distribution of your per strategies. In a polytope game, it doesn't have to be a simplex. Agents choose actions within polytopes. And in normal form games, like when you pick the simplex, it's very clear that the interpretation is a probability distribution over pure actions. But in the polytope game, the interpretations are numerous. So this can describe extensive form games, Bayesian games, other things too. Um, so I'm gonna skip to here and say that everything we just said about normal form games is also true for polytope games. We can still define a CSP in the exact same way. The key difference, though, is that before, when we looked at this CSP definition, which was a product distribution over the actions at every round, and then looking at the average over all time, it was an obvious disinterpretation, which was that it was a distribution of our pure strategy move pairs. That's no longer true. In polytope games, there's no distributional interpretation. The ijth entry is just a number that averages over time the value of the ith entry in the vector played by x and the jth entry in the vector played by y. Despite this, we can still define a menu the exact same way. And we can again say that there's a unique menu achieving no regret and non-manipulability in polytope games. So we have this notion called profile swap regret. And note importantly, we're no longer doing this thing where we try to come up with what is the right notion of swapping. There is a notion of swapping that is implied by this definition, but it's actually it's so unnatural that it's not even something I'm going to describe today. It turned out the right way to think about non-manipulability and swap regret beyond normal form games isn't to ask what is the right thing to swap. It's to ask how do we minimize, how do we construct non-manipulable objects and going from the definition rather than the swapping part. So we define profile swap regret as distance to this unique strategic menu M star that achieves no regret and non-manipulability. And it wasn't actually so obvious that this was enough. So we have this notion, but it turns out that you can't efficiently check membership in this menu M star, this non can easily check membership. Luckily, that's not the only way. And there was recent work in Stock 25, which characterizes times when you can, in fact, use certificates of approachability to construct an efficient algorithm to approach the set. And so that is a tool that we use in our work. And we actually do come up with an algorithm that efficiently approaches the set. I will just leave you with this note, which is that for those of you who are familiar with correlated equilibria, in normal form games, there's this nice thing where what is it? It's basically you have some mediator who is recommending action pairs, and the action pair that one person gets, given that, they know what the distribution of our action pair is, they have some prior over what the other person will be playing. And so the idea is I need to best respond to that, right? So that's the mediator view. And the learning view is that it's the time average CSP between any two no swap regret algorithms. And these are exactly the same in normal form games. But it's not true in polytope games. These notions are actually different. So in polytope games, if you take two, using our notion no swap regret, these non-manipulable algorithms in polytope games, and you look at all the outcomes that are possible between any such two, this is actually a strictly larger set than a set of things that are implementable by a mediator. Awesome. So I'm just going to flash the upshot here again. Thank you all so much for your time, and I'll end the talk here.